Okay. Myself, Dr. G. Venkat Subbareddy, Associate Professor in EEE Department. Today our topic is Symmetrical Component Theory. The three-phase, three unbalanced vectors can be replaced by a system of three balanced vectors. A system of three balanced vectors are, one is positive sequence component, the second one is a negative sequence component, the third one is zero sequence component. Assume that the three vectors are VA, VB, VC that can be represented in terms of positive, negative, zero sequence component. The advantages of symmetrical components are the calculations are making very simple and better understanding the problem by using these symmetrical components. Next, what is the positive sequence component? A positive sequence component is one which has three vectors equal in magnitude and displaced by each other by 120 degrees in the same phase sequence as that of a original vector. That is nothing but VA1 and VA2, that is VA1, VB1 and VC1. Equal in magnitude but displaced by 120 degrees in the same phase sequence as that of a original vectors. The second is a negative sequence component. Negative sequence component is one which has a three vectors equal in magnitude but displaced in opposite direction to the original vector. That is nothing but this is VA2, this is VB2, this is VC2, but displaced by 120 degrees with each other but in opposite direction. This is nothing but the positive sequence, this is nothing but negative sequence. The third one is the zero sequence component. Zero sequence component is one which has three vectors equal in magnitude but displaced in phase with each other. This is VA0, this is VB0, this is VC0. Every phase vector can be represented as sum of positive sequence component and negative sequence component and zero sequence component. Suppose the three unbalanced vectors VA, VB, VC that can be represented in terms of symmetrical components. VA is equal to VA0 plus VA1 plus VA2. VB is equal to VB0 plus VB1 plus VB2. VC is equal to VC0 plus VC1 plus VC2. Suppose phase A is taken as a reference. The phase B and phase C values in terms of phase A, for representation of in terms of phase A, for that reason we define an operator lambda. That can be defined as lambda is equal to 1 at an angle of 120 degrees. This can be written in rectangular form cos 120 plus j sin 120. Cos 120 is minus 0.5, j sin 120 is plus 0.86. Similarly, the lambda square is equal to 1 at an angle of 240 degrees. This value in rectangular form minus 0.5 minus j 0.866. Lambda cubed is equal to 1. Then 1 plus lambda square is equal to 0 and lambda cubed is equal to, these are the properties of lambda. By consider this lambda, then VB0 in terms of VA0 and VC0 in terms of VA0, VB1 in terms of VA1 and VC1 in terms of VA1 and VB2 in terms of VA2 and VC2 in terms of VC2. VA taken as a reference, the value of VB1 is equal to lambda square into VA1. The value of VC1 is equal to lambda into VA1. Similarly, the zero sequence component VB2 is equal to lambda into VA2 and VC2 is equal to lambda square into VA2. VB2 is equal to lambda square into VA2 and VC2 is equal to lambda square into VA2. Then the unbalanced vectors can be written as in terms of symmetrical component. VA is equal to VA0 plus VA1 plus VA2 and VB is equal to VA0 plus lambda square VA1 plus lambda VA2 and Vc is equal to Va naught plus lambda Va1 plus lambda square Va2. That means Va is taken as reference. The values of Vb and Vc in terms of Va, then Va is equal to Va naught plus Va1 plus Va2. Vb is equal to Va naught plus lambda square Va1 plus lambda Va2. Vc is equal to Va naught plus lambda Va1 plus lambda square Va2. Lambda square Va2. These three equations can be written in matrix form Va, Vb, Vc. That is nothing but a phase vector matrix. Then 1, 1, 1, 1 lambda square lambda, 1 lambda, lambda square into Va naught, Va1 and Va2. The above three equations can be written in matrix form Va, Vb, Vc, 1, 1, 1, 1 lambda square lambda, 1 lambda square lambda, lambda square, Va naught, this vector is nothing but a phase vector in compact form. This is nothing but a vector. A is nothing but a symmetrical component transformation matrix. This is nothing but a symmetrical component of vector. Suppose if you measure phase component in terms of symmetrical component, if you want to measure symmetrical component in terms of phase component in vice versa, then that values becomes Va naught is equal to 1/3 of Va, 1/3 of Va plus Vb plus Vc, and Va1 is equal to 1/3 of Va plus lambda Vb plus lambda square Vc, and Va2 is equal to 1/3 of Va plus lambda square Vb plus lambda. These two set of equations are very important for calculation of fault analysis also. And then we go for fault analysis. Fault can be classified into two types. Faults are classified into two types. One is nothing but a shunt faults. The second one is nothing but a series faults. Shunt faults is again classified into two types. One is nothing but a unsymmetrical fault. The second one is symmetrical fault. The unsymmetrical faults again classified into LG fault. The second one is LL fault. The third one is double LG fault. And the symmetrical fault is three-phase fault. In case of shunt faults, the current is increases, the remaining quantities voltage, frequency. In case of shunt fault, the current component is increases, then frequency, power factor, and power factor is decreases. Whenever the fault is occurs, in case of shunt fault, the current is only increases, frequency and power factor is decreases. And in the opposite direction, in case of series fault, current is decreases, the voltage, frequency and power factor increases. These are the characteristics of series and shunt faults. Series faults is, there are two types. One is one open conductors and two open conductors. Series faults is one open conductor. The second one is two open conductors. One open conductors and two open conductors. Major faults in power systems are 90% of faults in power systems are LG faults. Most severe fault in unsymmetrical faults is LLG fault. The severe symmetrical fault is three-phase fault. Next, LG fault. Fault takes place on IA. Fault is take the place on IA. There is no faults on phase B and phase C. There is no fault on phase B and phase C. And in case of LG fault, fault is takes on phase A. Then the boundary conditions are VA is equal to 0 and IB is equal to 0 and IC is equal to. And the three sequence network equations are VA1 is equal to EA minus IA1 Z1, VA2 is equal to minus IA2 Z2, VA0 is equal to minus IA0 Z0. These are the three sequence network equations. By using this three sequence network equation, again the phase component in terms of symmetrical components or symmetrical components in terms of phase component, VA0 is equal to VA plus VB plus VC, and VA1 is equal to 1/3 of VA plus lambda VB plus lambda square VC, and VA2 is equal to 1/3 of VA plus lambda square VB and plus lambda VC. By substituting these boundary conditions in these three sequence network equations, VB is equal to VC. Then substitute other two boundary condition in the symmetrical component equation, then we get in case of LG fault, IA0 is equal to IA1 is equal to IA2 is equal to IA by 3. Then IA0 is equal to IA1, that is equal to IA2, that is equal to IA by 3 in case of LG fault. That means the three sequence networks are connected in series in case of LG fault. The three sequence networks are connected. This is nothing but a positive sequence network diagram. VA1, IA1, Z1, EA. Negative sequence network diagram is Z2, IA2 and VA2. And zero sequence network diagram is Z0, IA0 and VA0. Because of, in case of single line to ground fault, then IA1 is equal to IA2 is equal to IA0, then the three sequence networks are connected in series. Then finally the fault current in case of single line to ground fault is IA1 is equal to, after completion of our analysis, IA1 is equal to EA divided by Z1 plus Z2 plus Z. Then fault current IF is equal to 3 IA1, that is equal to 3 times of EA divided by Z1 plus Z2 plus. Like this, we derive an expressions for LL fault and LLG fault. In case of LL fault, the fault current IF is equal to √3 into EA divided by Z1 plus Z2. In case of LLG fault, IF is equal to, IA1 is equal to EA divided by Z1 plus Z2 Z0 plus Z2 plus Z0. From under three phase fault, symmetrical fault, then IA1 is equal to EA divided by Z1. From the analysis of various type of faults, the positive sequence component Z1 is present in all type of faults. This negative sequence component Z2 is present all unsymmetrical fault. And zero sequence component is present when the neutral of the system is grounded and fault is also involves the ground.